Let us have a generalized form of a transfer function for any second-order mechanical system. A generalized transfer function in terms of a damping ratio and the natural frequency for given second-order mechanical system is given by a transfer function ys upon xs. In this mechanical system, it consists of a massless plate, a damper C, inertial body M, and the spring or elastic member of stiffness K. Now the input is given to the massless plate so that it will transfer this motion to the inertial bodies. Now it is very important to understand the input is given x, and what we are expecting, mass has to move with a response yt. So input is the xt and output of the system is yt. Both are along the axis and are translatory motion. Very important, the plate what we are having here is the massless. So only one inertial body is there having mass m, one dashpot C, and one spring K. Now it's very important, before writing a transfer function one should know what is the input given to the system and what is the response of the system or output of the system. Now if it is known to us xt is the input and yt is the output, then we can write a transfer function in terms of s as per the definition. It's a Laplace transform of output to the Laplace transform of input. So that hence we are having ys upon xs is equal to k dash into omega n square over s square plus 2 zeta omega n into s plus omega n square. So this gives the generalized transfer function of any second order mechanical system, and hereafter we are going to use this equation to solve the numerical, where k dash is constant, omega n is the undamped natural frequency in a radian per second, and zeta is the damping factor or a damping ratio. We'll just try to understand all these terms through the derivation. So we are going to derive by using mechanical system which has a second order, and through that derivation we'll try to understand how we obtain this transfer function as a generalized form. Let us move towards a derivation of second order mechanical system so that we obtain the generalized form of a transfer function. Now let us derive a generalized form of a transfer function in terms of a damping ratio zeta and the natural frequency omega n of a second order mechanical system shown in a figure. So this system, as we discussed earlier, it consists of a damper of a damping coefficient C, stiffness or elastic member of spring constant K, inertial body of a mass m. The inertial body is rolling over a frictionless surface, so there is no friction in a roller and the surface. The input displacement is given to the massless plate, and the displacement given to this massless plate is x. It is assumed that the mass is moving in the same direction of x. So we can say that the input given to the system is x and the output of the system is yt. So both are function of time. Now for this second order mechanical system, which consists of spring mass damper, we'll derive the dynamic equation first, and from that dynamic equation we'll get the transfer function, and once we are having a transfer function, we'll derive the transfer function in terms of damping ratio and the natural frequency after understanding the definition of a damping ratio and the natural frequency and the forces exerted on this mass. So let's assume that the mass is accelerating in the direction of y displacement. So accelerating force is acting in the direction of displacement, and that is m into y double dot. The role of damper and the spring, as we discussed, is to resist the motion. The mass is moving towards the right in the direction of y. So damping force is trying to resist the motion. So damping force will be given because the damper is compressed by an value y. So we'll say that the velocity in the direction of displacement y is y dot. So damping force is equal to c into y dot, which resists the motion by accelerating body. Similarly, the spring has a role to resist the motion. But here we'll observe that the mass is moving with respect to massless plate. So massless plate is moving with a displacement x and the mass moving with a displacement y. So we'll find the net deformation in the K is y minus x. So the spring is offering a resisting force on the mass is equal to spring constant into the net deformation taken place in this spring, and that net deformation is y minus x. So the spring force which is exerting on this mass is y minus x. So these are the forces which are acting on the accelerating body. Now by applying the Newton's second law, so we are considering the body is accelerating, and we'll say that the summation of all accelerating forces must be equal to summation of all other forces. which are acting on system. So accelerating force, what we are doing here, we are assuming the sign convention. If the force is acting in the direction of accelerating force, will be considered as a positive or otherwise will be negative. So accelerating force, it is m into y double dot is a positive, is equal to minus c into y dot. Since damping force is acting in opposite directions, so minus k into y minus x. So if we rearrange this equation, so we'll get my double dot plus cy dot plus ky is equal to kx. So this equation is a dynamic equation or the governing equation of given second order mechanical system. Now we'll rewrite this equation in the known format, m d2y by dt square plus c dy upon dt plus k into y is equal to k into x. Now by applying the Laplace transform to the differential equation of a given system, so we are applying the Laplace transform as we discussed in the last numerical, so we'll get ms square y of s plus. Okay, now the next terms will get cancelled out because we are applying the initial conditions. As per the definition of transfer function, the transfer function is the ratio of Laplace transform of output to the Laplace transform of input, considering all initial conditions set to the 0. So after setting the initial condition to the 0, these terms will get cancelled. So what we are having, ms square into y of s plus c into s y of s plus k into y of s is equal to k into x of s. Now we'll take y of s common from this equation out of bracket. Y of s in bracket ms square plus cs plus k is equal to k into x of s. Now we can apply definition of a transfer function. We'll take a ratio of y of s to the x of s will give us the transfer function of given second order mechanical system. So transfer function is equal to y of s to the x of s is equal to k over ms square plus cs plus k. So this gives a transfer function of given mechanical system. Let us write this equation as b and this equation as, where k is spring constant. For a linear spring in a translatory system, the unit of spring constant is Newton per meter. C is the damping coefficient. For a linear system, unit of a damping coefficient is Newton second per meter, and m is the mass of accelerating body in kg. Now next, we'll try to understand the definition of a damping ratio zeta and the natural frequency omega n, and we'll apply this definition and we'll write a transfer function in terms of damping ratio and the natural frequency, and thereafter we'll convert that equation as a generalized form of a transfer function in terms of a damping ratio and the natural frequency of any second order mechanical system. So we can use that equation for any second order mechanical equation as a transfer function. Now let us try to understand some definition. A damping ratio or a damping factor is also called as a zeta, symbolically represented by the symbol. The damping ratio is the dimensionless quantity characterizing the rate at which the oscillations in the system's response decays due to the effects such as a viscous friction or electrical resistance. In other words, we can define the damping ratio is the ratio of damping coefficient to the critical damping coefficient. So zeta will be equal to C upon Cc, where C is damping coefficient and Cc is the critical damping coefficient. So critical damping coefficient Cc is equal to 2m omega n, where omega n is the circular natural frequency of oscillatory system. M is mass of the system. A unit of critical damping coefficient is same that of damping coefficient, Newton second per meter for a translatory system. So damping ratio is dimensionless quantity since it's a ratio of same parameter damping coefficient to the critical damping coefficient. Next, a natural frequency. Natural frequency omega. Generally, natural frequency is defined for undamped free vibrating system. The frequency of undamped free vibrating system is generally called as the natural frequency of a system, which is represented in the radian per second. So natural frequency omega n is the frequency in a radian per second that the system will oscillate at when there is a no damping, there is a no resistance. That means our system is undamped. In other words, we can say that zeta, or the damping ratio, is equal to 0. So natural frequency can be written in terms of omega n square is equal to k by m. So we can have omega n is equal to under root k by m. The unit of circular natural frequency is radian per second. Now let us derive the generalized form of a transfer function in terms of damping ratio and a natural frequency of a second order mechanical system. By understanding these definitions of the concepts, now we can apply this concept to get an equation of a transfer function that we derived earlier for the given system. So let us derive that equation in terms of damping ratio and natural. Let us rewrite the transfer function. Transfer function is equal to y of s over x of s is equal to k upon ms square plus cs plus k. Now we have to write this transfer function in terms of a damping ratio and natural frequency. So for that, from a denominator equation we will take m common out of this equation, then k over m into s square plus c upon m into s plus k upon m. As per the definition, we know that k upon m is omega n square, and omega n is circular natural frequency of the system. Now to find c upon m ratio in terms of zeta and natural frequency, c upon m we have to write in terms of zeta and natural frequency. So we'll just modify this ratio as c upon cc, dividing and multiplying by cc. So will not affect on this ratio, but we know that by definition c upon cc is the damping ratio, and cc value is equal to 2m omega n over mass. So mass get cancelled. So we got c upon m is equal to 2 zeta omega n. So we'll substitute this a and b in above equation, equation number 1. So what we'll have, y of s over s of x is equal to k upon m over s square plus c upon m s plus k upon m. Then we'll substitute a and b in this equation. We'll get omega n square over s square plus 2 zeta omega n s plus omega n square, y of s over s of s. So this is the transfer function in terms of natural frequency and damping factor or damping ratio. Now let us write this equation as a generalized equation or in a generalized form of a transfer function for all second order differential equation. So we can use this transfer function for any second order mechanical equation as a transfer function by substituting the values. Provided the system should have damper, spring and mass as a basic three elements. If it is not, if the damper is absent, so we will substitute zeta is equal to 0, and then we have to modify this equation for the given second order mechanical system. So we'll write generalized form of transfer function for second order mechanical system. So transfer function is equal to, we'll write it as k dash into omega n square over s square plus 2 zeta omega n into s plus omega n square. So carefully if you are observing, it's a quadratic equation and the last quantity in the character equation is also present in the numerator as omega n square, and k dash is any constant or the gain value. So this gives a generalized form of, this is the transfer function of any second order mechanical system. So we'll use this transfer function to solve a numerical, and we have derived the equation that we discussed before starting this session. So we'll find the roots of character equation, and based on this root we'll have three different systems: overdamped system, underdamped system and critically damped system, and we'll just try to understand the importance of a zeta while defining these three types of a system. And out of this one, underdamped system possesses some oscillation, and that will be case of study since the oscillations are still present in that system, but still we are expecting the system response should be as fast as possible. So we can write this transfer function in terms of tau or t represent the natural period of oscillation in second, and natural time period t is equal to 1 upon omega n. So we'll rewrite this transfer function in terms of tau by taking omega n common from the characteristic equation, denominator equation. So what we are having, a transfer function is equal to k dash omega n square over, we'll take omega n common, omega n square in a bracket, it is 1 upon omega n square into s square plus 2 zeta into s over omega n plus 1. So here omega n square get cancelled, and we know that 1 upon omega is equal to natural period of oscillation t. So we'll substitute that value and we'll get another form of a transfer function in time period. So it is k dash over tau square s square plus 2 zeta tau into s plus 1. This is the another form of a transfer function in time period. Our next discussion will be to get the roots of this characteristic equation, and based on these roots we'll classify the response of the system at a different zeta values. So we'll get three systems, one is overdamped, critical damped and underdamped system, and also we'll just find for these three different systems for step input function how the system responses and their root location in S plane.